Hello students. So let's start with a revision of haloalkanes and a haloarine. And here is the first question. So since this is organic, I may go into a little depth of the topic, like how to do the reaction. See, there is no point in just writing a general reaction and getting the answer. This video may be for a great learning for you how to deal with the organic chemistry, right? So we'll take this first question. The question asked here is the position of the Br, okay, in a compound. Okay, there is a compound which is given this way. There is this compound which is given this way. Now, what does it mean? The first thing is that we should be able to break open this structure. Means there is a first carbon, it is this, and it is having three hydrogens. You can see that there are three hydrogens on it. You will break open it this way. This is hydrogen, this is hydrogen, and this is hydrogen. Then next there is one carbon, again it is connected, this carbon I mean, and there is a hydrogen to this, and there is a double bond. There is a double bond, right? And there is one more car hydrogen connected to that. Then next there is a carbon, and to this carbon there is a Br connected. And then there are two CH3. This bracket, no bracketed term means it is connected to this carbon. So this is what it means. This is the structure. So now the question asks position of the Br in the compound given can be classified as, okay, the options given are allylic, vinylic, aryl or secondary. Okay, here it is not secondary because it is like, see, the compound may be secondary and as well as it can be allylic. It can be secondary as well as vinylic. That possibility is there. So more thing what we should focus is whether it is allylic, vinylic or aryl halide, right? So here, what is the meaning of the allylic? Allylic means this halide is connected to sp3 carbon, right? Halide is allylic means halide is connected to sp3 carbon. Let's take this way. If it is this, I can show this same structure this way. C, CH3, CH3, and this is the CH3. What is the hybridization of this? It is connected to sp3 hybrid carbon, sp3 hybridized carbon, and next carbon connected to is this is a sp2. So whenever it is connected to allylic carbon and next to that is sp2 carbon, such kind of halide, sorry, this is Br. This is Br. Such kind of halide is called as allylic halide, right? And vinylic halide means Br will be directly connected to a double bond. Br will be directly connected to double bond. It is if it was this way, if it was this way, Br is directly connected to what? Carbon. This is vinylic. This is allylic. Aryl means halide, halide getting directly connected to benzene. Means this Br is directly connected to benzene. That is what the aryl. So the answer over here is allylic halide. Now, many students must be having the doubt how to identify the hybridization. I'll tell you the trick. I'll tell you the trick. Trick is very simple. If it is a double bond, if there is a carbon-carbon, we'll start with this. If there is a carbon-carbon single bond, and any species which is connected to this, or whenever there is a carbon-carbon single bond, or all bonds connected to carbon are singly, okay, single bonds are there. Then it is what in this case, in this molecule itself, let's say this carbon is if you see there are four single bonds connected, so it is what it is sp3 hybridization. Okay, it is sp3 hybridization. If there is a carbon carbon double bond, carbon carbon double bond, both these carbon there is a double bond in between them, so hybridization of both these carbons is sp2. Okay, and if there is a molecule like this, which includes a triple bond also, if it is including a triple bond, means molecule is this. So both the carbons over here are sp hybridized. Okay, these carbons are sp hybridized. So carbon carbon triple bond means it is sp hybridized. So this is how you can easily identify the hybridization. Okay, and this is how easily you can identify the hybridization. Okay, next question. Let's take this question. Question ask is carbon carbon bond is polarized because option. What is the meaning of polarity? What is the meaning of polarity? Polarization. Polarization takes place takes place due to uh, presence presence of electronegative electronegative element. What is the meaning of polarization? What is the meaning of polarization? Polarization is charge separation. It is a charge separation. This is what the polarization is. Okay, nobody is going to ask these definitions for you, but you should know these concepts. So polarization takes place due to electronegative element. What is the electronegative element? I am writing the definition of each and everything so that you can recollect all the things what you have done in 11th standard. So this electronegativity means electronegativity means it is tendency of an element to attract shared pair of electron towards itself in covalent bond. This is what the electronegativity. Examples which are the most electronegative halides like fluorine, chlorine, bromine, iodine, astatine, oxygen. Till here it is a halides. Then oxygen is also electronegative, nitrogen is also electronegative, sulfur is also electronegative. Okay, these are the elements which are the most electronegative element. Means these elements will have the tendency to pull the electron towards itself. Means what? If there is a bond like this, if there is a carbon and the halide bond is there, carbon halide, covalent bond, it is a bond formed by sharing of the electron, right? So this is the covalent bond and this is the halide. And let's say this is the three hydrogen. Let's not worry about this. We'll focus on carbon halide bond because X is a halide. It is like this is what the sharing we feel. But in real case, what will happen is that this electron which is there, no, it will be more in the side of the halide. This electron will be more in the side of halide. So what will happen that this negative charge, this halide is going to have a partial negative charge and this carbon is going to have a partial positive charge because electron has gone away from the carbon. So this carbon is losing its electron. Partially it is losing. So partial positive charge and partial negative charge. Okay, there is current has gone just now. So this is what the polarity and it is due to electronegative element. So answer over here is that carbon halogen bond is polarized. Answer, someone can comment what could be the answer. Answer is halogen atom is more electronegative. Halogen atom is more electronegative than carbon. This is the reason, right? So okay, let's continue student with the next question. Question asked is which reagent will you use for the following reaction? See this example, if you see over here, it is direct example of the free radical halogenation. It is an example of free radical halogenation. Okay. How free radical is formed? Due to homolytic cleavage. Homolytic cleavage, a very good example. If you want to, this is something you can always remember. Homolytic cleavage, to happen homolytic cleavage, you should use a UV light. Okay, homolytic cleavage. Homolytic cleavage means, okay, I'll tell you about the cleavage, breaking of the bonds. Homolytic cleavage means this. Let's say there is an atom. there is an atom A. If I take A, let's take this. Uh, okay, there is an atom A and there is atom B. Okay, so if this bond is breaking, then if this is the arrow, full-headed arrow, means the electrons which are over here, this electron is of A and this electron is of B, is going with B. And what you will be getting is that A plus, because A is losing the electron and B is gaining the electron. So B is going to have a B minus. So this cleavage what I have shown is a heterolytic cleavage. This is what is not formed in this example. What is homolytic cleavage? Let's say A and B, and this is the electron over here of both the species, and this is how the bond is going to break. We are going to show a half-headed arrow. This is the half-headed arrow which we show, right? So this leads to A plus B with the free this lone electrons. Yeah, it is not lone pair, it is just lone electron. So this is called as a free radical. This is called as a free radical formation. Free radical formation. And who can do this? Uh, this can be done in the presence of light. You can use a UV light for this. On this arrow, I will show UV light or heat. Or in some cases, it will be just written H nu. H nu represents a light. So chlorine and a UV light. So this is an example. Directly chlorination is done using a free radical halogenation. Uh, so free radical halogenation takes place in a three steps. There is a process of initiation, there is a propagation, and then there is a chain termination. Many steps are there, but here two kinds of free radical. If you take this example over here, I'll open this structure and show you. There will be a two possibility for a showing a homolytic cleavage. Actually, before I start, before I go into the mechanism, uh, yeah, start of the mechanism. It will not start here. It will start here. This chlorine, which I'll tell you the answer here. This is the chlorine. This is the answer actually, because it is a chlorination. You are adding a chlorine, substituting a chlorine. So chlorine bond, both will have same electronegativity, right? Both are having same electronegativity. So this bond will be broken equally. This bond is broken equally, and that is in the process. If you supply a UV light or any light, or you can say just H nu. H nu represents a light. So this will lead to the formation of a free radical. Here there is a free radical formation, right? This is the free radical form. So first step is a formation of free radical. Okay. Step two is what? Now this free radical which is formed is unstable. They are unstable. Something which is unstable will always try to react. Since this is unstable, it will try to react. Where it is going to react? It is going to react over here. CH3. Like this is the step where the initiation is done. So it is going to react here. Let's take this here. CH3, right? So this is the free radical which is going to react either here. First, I'll show most stable attack where it is going to go and do the attack. That's what the stable attack I am going to show. This is the free radical, means this is going to attack and over here, and this is going to try to form a new molecule which is HCl. Now this is also having a free electron, lone electron. There are two electrons over here. So this one electron and this one electron will form a bond, and there will be free radical formation on this carbon. So this will lead to the formation of free radical like this. CH3, CH2, CH, and this is the free radical. And the other possibility is that free radical can react with this carbon also, right? So this will lead to another kind of free radical, that is CH3, CH2, CH2, and CH2, and here is the free radical. right? So what happens in this process? There are two kinds of free radical. This is a secondary free radical you can identify. This is secondary free radical, and this is primary free radical. A stability of free radical, I'll write over here. Stability of free radical is in this order. Tertiary is more stable than secondary, and least is primary. So among this secondary and tertiary, this is more stable. So this will be our major product. That is not us. I'm just revising this. This will be a major product, and this is minor product. So this is not the final product, but another Cl minus which is there. Obviously, that Cl minus, not Cl minus, Cl free radical is going to combine with this, and possibility is there. There is one more Cl free radical which will combine with this to form this product, and that's the whole idea about this. And the answer is this already given. Hope everyone must have understood this. Next question is which of the following is a halogen exchange reaction? See, there are two halogen exchange reaction you learn in your organic chemistry. Halogen exchange reaction. That is, one is a free radical. Sorry, one is a Swartz reaction. Swartz reaction. This is halogen exchange. This is for the preparation of the fluoroalkane, and other is a Finkelstein reaction. Finkelstein reaction. Just check the spelling. It is this. This is for Swartz is for preparation of fluoro fluoroalkane, right? And this is for preparation of iodoalkane. Okay, that is two things we are learning. Here, if you see alkyl halide, this is a alkyl halide, you are getting a alkyl halide. So here this iodine is getting exchanged with this, right? So that's why I guess first should be the answer. Yes, this is a halogen exchange reaction. Here halogen is not getting exchanged. Here H is getting added. This is a addition reaction. This is a addition reaction. It is not exchanging. Means this is a carbon carbon double bond. Means there is a hydrogens over here. What happens is that you add a HX, one hydrogen will go here, one halide will go here, and double bond will go. See, the thing is somehow we have to maintain four bonds of the hydrogen. So this is what you are going to get. This is addition reaction. Here it is substitution reaction. If you see, this is a substitution reaction. Substitution reaction. Why? What is happening in the option B? Substitution. Why? Sorry, option C. It is R OH, and this is HX. So what happens at the end? Alkyl halide substitutes OH. So R X you get, not a halogen exchange. And here also, this is a electrophilic substitution reaction. This is electrophile as a X plus gets substituted on this benzene. Option D is electrophilic substitution reaction. Electrophilic substitution reaction. So the answer is option A. Next question. Uh, Among the isomeric alkanes of the molecular formula C5H12, okay, this is what the molecular formula C5H12, identify the one that photo on a photochemical chlorination means free radical halogenation. Photochemical chlorination means it is a, remember, it is one and same, free radical halogenation, one and same it is. Okay, means they are like question is telling us to identify the structure, what are the isomers possible for this, and just tell me like answer is how many, identify the one that uh, identify the one that on photochemical chlorination yields single monochloride, three isomeric monochloride, and four isomeric monochloride. First, let's understand how many isomers are possible for this. Okay, first is this one, two, 3, 4, and 5. This is a straight chain isomer. Means to maintain the valency of the carbon, that is 4, I am putting this 3 hydrogens here, 2 hydrogens, here also 2 hydrogens, 2 hydrogens, and this is CH. This is a structure. Now you just imagine that, okay, this is the first isomer possible. Second isomer possible is this, right? 1, 2, 3, and one carbon will come over here. Means this is the second CH3, CH3. Here there is just one hydrogen is required because now it is satisfying the valency. Here 2 and here it is 4. This is the second isomer which is possible. Third isomer which is possible is this CH3, 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 CH3. Isomer definition, same molecular formula but different structural formula, right? It is a relation between these three is they are a structural isomer. They have same molecular formula of C5H12, but they are having a different uh, structural formula, same molecular formula and a structural formula. So you can try that if there are any more other structures, there won't be any more structure possible out of this C5H12. So if I take a first example, if I take a first example of this, okay, you can just make a note of this. You can just make a note of this because I am going to clean this space. Uh, we are having this three isomer. Just make a note of this because I am going to utilize this space. And let's do the chlorination now. You will get your answers. You will get your answers. Let's do the halogenation on each of this. The first isomer which I was having is this, right? CH3, CH2, 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 and CH3. A chlorination, a chlorine is there, and you are putting, let's say, UV light, free radical halogenation. Now the possibility of the free radical formation, the earlier case, um, I think there was just two possibility. Here there are three possibility of the formation of the compound. Means chlorine can get substituted here, it can get a substitute here, and it can get substituted over here. If it is getting substituted here, it is one and same, and if it is getting substituted over here, it is again the other compound which is same, right? So here there are these compounds. So at 1 carbon will start. So first I am substituting on this. So possible product is this CH3, CH2, 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 and CH2Cl. This is what the one possibility. Second possibility is this CH3, CH2, Cl, and here it is CH3. Third possibility CH3, CH2, Cl, CH2, and CH3. Fourth possibility, is there a fourth possibility? Let's write a fourth possibility also. Cl, CH2, CH2, and CH3. Fourth possibility, and this. Both are one and same. Both these structures are one and same. This and this, right? So we'll not consider this, and even the last one will not consider because last one and the first one will be same. Yes. So first compound on a free chlorination, free radical halogenation is going to give you three compounds, right? So what is the answer? Three isomeric monochloride. So identify the one that yields three isomeric isomers. So this is that compound. Name of this is N-pentane, right? N-pentane. Okay. What about second structure which I was getting? Second structure what I was getting was this. Second structure was this. CH3, CH2, CH2, CH. Sorry. Second structure what I was getting was this. Right. So what are the possibility of the free radical halogenation? Chlorine and UV, right? So you will substitute here and here. Let's write all the possibility and then we'll check which are common. Okay, then we'll check which are common. So here, possibility for this reaction, possibility for this reaction, one compound, what it will show is this CH2, CH2Cl, and CH2, sorry, CH3. This is one possibility. Second possibility is this CH3, CH2, CH, CH3, and this is CH2Cl, right? This is the second possibility. So both these compounds are actually same. If you do the IUPAC nomenclature, the names of these both the compounds will be same. So I'll consider this both the things to be one, or will not consider this. Okay, will not consider one of this. So this is my first compound. This is just one compound I'll consider. It is not, they are not different. They are same compound. So I'll clean one of the compound, right? We'll do this. Second possibility is that we can have a second compound, chlorine getting substituted on this. So this is CH3, CH2, CH3, CH3, and Cl. This is second possibility, right? And the third possibility is this of the free radical chlorination, CH3, CH, Cl can be over here. This is CH, CH3, and CH3. Then fourth possibility is this. So this is fourth possibility. CH2, Cl, right? So which compound is giving you this? Four compounds. Four isomeric compound is this. Means answer for this is this, right? And three single monochlorides. Single monochlorides means I'll clean this. Just note this down. Third compound which I was getting was this. Third compound was this. CH3, 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 and CH3. See, all the carbons are equivalent. Wherever you substitute, wherever you do the chlorination in the presence of UV light, like whether you are substituting here, 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 or here substitution is not going to take place. The hydrogen is not there. There is no hydrogen. So substitution possible is here, 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 here. Means the possibility is this CH2. Even if it is getting substituted over here, it is one and same. So only one product you will be getting. Means other products I'll write. It is this. Second product is this. But it is same as the first one, right? You try with any other carbon. The third possibility may be this. Third possibility is this. Again, all these compounds are same. Fourth possibility is this. So it is one and same, right? So for single monochloride, who gives you single monochloride? This compound, CH3, CH3. This gives you single monochlorides, one of the isomer, right? Three isomeric monochloride was given by this CH3, CH2, 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 and pentene. And four isomeric chloride was given by this CH3, CH2, CH, CH3, and this. So you can write the IUPAC name and comment in a chat box. Okay, comment below this YouTube video. What are the IUPAC names of this? I will be happy to receive your comments. Okay, let's take this example again. Question asked is toluene reacts with a halogen in the presence of iron 2 chloride. Iron 2 means 3, sorry, iron 3 it is. 3 means it is the oxidation state it is representing. Giving ortho para halogen compound, the reaction is. First of all, I'll write the reaction. First, I'll write the reaction. Reaction is this. This is what the toluene. This structure, what I have written is toluene. Okay. It is reacting with what? Halogen. Okay, let's say chlorine it is reacting. If it is reacting with a chlorine in the presence of FeCl3, the product will be what? Product will be Cl. This is major product plus this is minor product. This is the reaction. Now, what is this reaction? This reaction is called electrophilic electrophilic substitution. Electrophilic aromatic substitution. We are substituting on a aromatic electrophilic aromatic substitution. Electrophilic aromatic substitution. So electrophilic aromatic substitution means what? There are two steps. Step one is a formation of electrophile. Formation of electrophile. What is the electrophile? Electrophile is electron deficient. Just write this. Electron deficient. Electron deficient means species like which are having the whose octet is not complete or who is having the positive charge. Mostly positively charged species are electrophile. So what will happen? How the electrophile is formed? The reaction between a chlorine, reaction between a chlorine and FeCl3, FeCl3. Okay. Now there is a reaction. Now I'll write this chlorine in this way also. I can write this chlorine Cl2 molecule, chlorine and a chlorine, and chlorine and the chlorine, and this is Fe, chlorine here, and this is the chlorine, right? So this Fe is electron deficient. Reason is its octet is not complete, like 1, 2, 3, 4, 5, 6. There are just 6 electron in its outermost core. And one more thing is that this is connected to halides which are highly electronegative. They are pulling all the electrons of a Fe. That's why this electron deficient. This Fe is a electron deficient. Over here, Fe is electron deficient. Electron deficient means it is in need of electrons. So what will happen whenever something's electron deficient species, who will donate? There is a pair of electron over here. It will be getting donated to this. Okay, it will be getting donated to this Fe. Means this bond is who is losing? Let's say this chlorine is losing, and this chlorine is getting connected to this. Over here, you will get after the reaction, what you are going to have is Fe, Cl, Cl. This is Cl, and this is Cl. Just take care. My Cl looks like a U. You can please try to understand. This is Cl. So now this is minus. Now who is losing? One extra chlorine is there. No, this chlorine is the plus. So this is my electrophile now. This is what the electrophile is. Okay. This FeCl3 is also called as a Lewis acid. Remember, FeCl3 is also called as Lewis acid. Okay, if you check in the equilibrium topic of the 11th standard, Lewis acid definition is a acceptor of electron pair, right? We got the electrophile. This is what I wanted. Step 2 is a substitution of the electrophile on a benzene, right? So I'll take you to the next page. We'll copy this question here. So I'll take this question here. Substitution. Next step 2 is substitution of electrophile on what was that? Toluene. Let's write over here toluene. Even if it was not a toluene, just understand. If it was just this benzene, if it was this, and this is the electrophile E plus ion, it can get substituted to any position. It can get substituted to any position. You will get a electrophile E getting connected to any position. It is one and same. Okay, any of the electrophile is always like here. In this case, you write it here. It is same. You write this E over here, it is one and same. Anywhere you write, it is one and same. But now it's not just a benzene, it is a toluene. Now the substitution won't be same. Anywhere you can substitute, it's not that way. So now it is a toluene. Now it is a toluene. So what is this toluene is known for? Toluene is known for a directive influence. This is ortho para directing group. Ortho para directing group for a electrophile. If there is an electrophile, the incoming electrophile will go at either at a ortho position or at a para position. Understand this. So from where you will learn this, like there are many groups, alcohol. Alcohol is also ortho para. NO2 is meta directing group. You just understand this from the basic concept. The concept I'll just make a note over here. It is a directive influence. It is a directive influence. Influence. You can study it. Directive influence of groups. Okay, on a substitution on a benzene, substitution of the electrophile on benzene. So where the incoming electrophile, where the chlorine plus will go either here, right, or here. So major product is this. Major product is this. Cl. And the minor product is this. This is minor, lot of repulsion, less stability. Here, major repulsion is less, more stability. Now, hope you are not getting these questions like, okay, only one chlorine is there. How come two products are forming? See, it is not that like chlorine molecule. There will be very large number of the chlorine electrophiles. Understand? If there is a water bottle, there is, let's say there is a glass of water. Just take this example. There is a glass of water. How many water molecule? Very large number of the water molecules will be there. Okay, so here I have taken this chlorine. Let's say 1 lakh chlorine ions are there. 1 lakh chlorine electrophiles are there in that solution. So what will happen? Around 70,000 or 80,000 will get substitute over here, and 20,000 will get substitute over here, right? It's that way. So answer is the reaction is electrophilic substitution reaction. Here hydrogen is replaced. Here there on every carbon there is a hydrogen. No, in the benzene, if you see the benzene structure, if you see the benzene structure, it is this way. We are writing a bond line structure, but it is this, no? One hydrogen is there, and this is carbon. So hydrogen is getting replaced over here, substituted. Hydrogens are getting substituted. So answer is electrophilic substitution reaction. Option B will be correct for this.